get started then. Thank you for coming along first, for starters. It's really lovely to see so many people. I know most of you have had quite a long day at work already as well, so thank you so much for sharing your time this evening. So my name is Dr. Kelly Bittner, and I'm going to be your facilitator this evening, speaking about maths and science in family daycare. So before we start, I just wanted to acknowledge the traditional owners of the country on which we're meeting today. So I know we're on many different lands with many different traditional owners, and I'd like to acknowledge them and also to recognise their continuing connection to land, waters, and culture. And I'd like to pay my respect to the elders past and present. I acknowledge that Aboriginal families have cared and educated children on this land for tens of thousands of years. So yeah, please feel free to pop in the chat the country that you're joining us from this evening, or maybe just think a little moment on that if you're more comfortable doing that. Okay. So some of the key messages to share with you. Many of you would have already been to other PD in your pocket sessions, but just a reminder that it is funded by the New South Wales Regulatory Authority, New South Wales Department of Education. We're just hoping that everybody got a copy of the resource booklet that goes along with this presentation tonight. So we did send a link through to that, and it will also be posted on the PD in your pocket Facebook page. If you didn't receive it for any reason, you'll be able to find a link on the screen if you're watching, or a recording of this presentation. If you're watching a recording of this presentation. If you're listening as a podcast, the link is www.nswfdc.org.au/PD in your pocket. So also just a reminder that you'll be sent information after this session, and if you could please fill in the surveys, because that helps to get funding that's very much needed to continue providing this training for free. And a big thanks goes out to everybody who filled in last month's survey. There'll also be certificates of participation mailed out, and make sure to check your junk mail if you still haven't received it. And you can also contact New South Wales Family Daycare if you still haven't received it. Okay, so let's get started. Here's what we'll be talking about tonight. We'll be talking about maths and science and how we can teach it with young children. We'll also be looking at mathematics for very young children, so in that birth to 3 age group. We'll hear a wonderful interview with an educator who's sharing her experience with maths and science in her family daycare service. And then we'll open up to some questions and discussion around maths and science. Oops, sorry. So thank you to everybody who took part in the questions when you were registering for this session. Here's what we learnt from you. When you were asked about how you feel about maths and science, we got this overwhelming response of that you love it. We got a smaller response of don't love it, and then a smaller segment of unsure. Now, this is really interesting and really reassuring, because a lot of the research shows that people who work in early childhood often don't feel very confident with maths and science. So we're in this presentation tonight, we're turning that research upside down. And I think that really comes through in the interview that you'll hear later on this evening as well. So I think it's an unrecognised area of strength, perhaps, within our sector. Thinking about the connections with maths and science in terms of the EYLF and My Time Our Place version 2.0, we can see again that people were really clearly able to see those connections, and that's great as well, to be able to see that it's embedded and a really important part of the EYLF and My Time Our Place version 2.0. And more learnings from you. So here we see when asked how often you include maths and science experiences in your program. Mostly we can see sometimes, and then almost the same, but not much less is every day. There's a tiny, actually the 0% for never, so everybody does, and then there was 3% of unsure. So this is great. As we're going through tonight, what you'll probably see in the information that we provide will really reinforce just how much you're doing throughout the day in terms of maths and science. And hopefully it'll give you a few more ideas of different directions you can take it in as well. So let's think for a moment on why early maths and science is so important. So as early childhood educators, we all know that the first 5 years are that critical time for learning and development. And we also know that the first 3 years in particular are even more important for brain development, that's the key time in our lives where the most brain development happens. We also know that mathematical thinking and scientific thinking happens for children from infancy. So it's embedded in their everyday experiences, either in their play or in the routines that happen throughout their daily lives. So through these experiences, starting from the earliest of days, that's when children have the opportunity to continually build their foundational understanding of maths and science that they'll continue to build on throughout their lives. So of equal or perhaps greater importance alongside those skills is the dispositions that young children develop during this time. So that's whether they see themselves as capable and strong mathematical and scientific thinkers, and whether they learn to see and really hang on to that joy and wonder that we can see in early maths and science. And sometimes that falls to the side when we get into school and things change a bit. So that's what we're aiming to do in the early years, to capture that joy that's associated with it. So when we look at maths and science, they're both made up of things called concepts and processes. Now, the key concepts are the big ideas or the foundations for mathematical and scientific thinking, and the concepts are what is learned, so the content. But then we also have the processes, and this is how learning takes place. So the processes are the action, that's what we do. So in this session, we'll talk through all of the concepts and we'll show how they're relevant and embedded in our teaching and everyday experiences with children. So to start off with, we're going to look at mathematics. Now, most people here felt quite confident with maths when they were responding to that survey. But we know often when we're talking with families or even often with other educators that maths can be sometimes something that just isn't something that they enjoy or that they feel confident with. And I think it's because if we think about maths, or if we say, for example, I just typed in a Google search of mathematics and this is what comes up. So what we see is lots of complex formulas, lots of numbers, and I think this is a fairly good indication of what a lot of people think maths is. So I know when I talk about maths for children birth to 3 with people, their initial response can often be, well, why would you do that? It's because they're thinking of this sort of maths, not the sort of maths that we understand and the sort of maths that we'll be talking about tonight. It will look like this eventually, but we get the really fun, wonderful maths to do with them, with children. So let's think about how mathematical thinking and learning fits within the EYLF. So the EYLF, it speaks quite a bit about maths in a number of different ways. It defines being numerate as the capacity, confidence, and disposition to use mathematics in daily life. So you can see that's quite different to that idea of formulas and quite complicated maths that first comes to mind. And this is the sort of information that we can share with families too when we're advocating about the importance of maths in young children's lives. The EYLF also provides us with this definition. It talks about, in terms of defining mathematics and numeracy, it says that it broadly includes understandings about numbers, patterns, measurement, time, spatial awareness, and charts and data, as well as that mathematical thinking and reasoning and counting. And I think this is really important because we also, from being a teacher for many years and an educator in early childhood services, I found that a lot of the focus was often on counting, but it doesn't reflect sort of that really the breadth or the diversity of different sorts of mathematics that we can focus on and that we do focus on with young children all the time. Sorry, I'm just catching up on my notes here. So what we're focusing on here is that we're supporting children to develop number sense and the ability to be able to draw on maths concepts and processes in ways that helps them be actively involved in their lives. It's about us asking questions and extending their thinking, and also about providing resources and experiences that help them to test their ideas and to demonstrate and reinforce their understanding. So let's look a little bit more about how maths and science is embedded throughout the EYLF. So this is just some examples from Learning Outcome 4. So also a little bit there from Learning Outcome 1. We'll see here that it features in what we might see in practice and also in the things that we could do to extend children's thinking and learning. Interestingly, we often see mathematical and scientific thinking together here. So we'll see, for example, the second point down from the bottom there that's highlighted. It says, use a range of strategies and digital tools to organize and represent mathematical and scientific thinking. Excuse me. And we can also see over the other side of the second column there, it talks about modeling mathematical and scientific language. So we'll be going through this a bit more in the presentation tonight as well, thinking about how we use those inquiry skills in maths and science and also the language that we use with children. But this is just a bit of a snapshot of ways that we can see maths embedded in the EYLF version 2.0. Now, let's also think about some of those terms that we use a lot every day in our practice, because sometimes it's good just to check in what we mean about them. It helps us when we're talking with families. It helps us when we're doing our documentation as well. So when we talk about intentionality, the EYLF defines this for us as being thoughtful and purposeful in actions and making decisions. And it's something that both children and educators can do. So when children are intentional, excuse me, when children are intentional in their thinking, their ways of communication and learning, and at times leading their own learning and the learning of others. When educators are intentional, we see this take place in the role they take in children's play and the way they intentionally plan the environment and the curriculum experiences. So I know all of you are very, very familiar with being intentional in your teaching practices, but yeah, just a bit of a reminder of what the EYLF tells us about it. Okay. So moving on to our maths concepts. So these maths concepts here aren't unique to early childhood. These are the ones that feature across all mathematics. So they are also underpin the key learning areas in the Australian curriculum, the New South Wales syllabus. They're what we focus on in early childhood as well. And you can see they also align with that EYLF version 2.0 definition of what maths involves. So in looking at these, you can probably think of many different ways that they're embedded in your day. But we'll go into each of them in just a little bit more detail now. Actually, we won't. First of all, we'll just go through the maths processes. So remembering that the maths processes are how we do mathematics with young children. So one of the things that we know we do all day, every day, is that we're observing and we're talking about what we see. And with that, we're making connections, we're maybe predicting what might happen next. Perhaps we're hypothesizing, so we're coming up with ideas that can be tested. And you can probably think of a million different examples of times you've asked those questions with children. Now, what do you think will happen if we do this? Or what might happen next? More specifically to maths, there's or mathematization, which is where we look at creating mathematical problems from real life situations. So this is where at any point in our lives where good maths learning takes place is where we actually see the maths being embedded in something that's useful and relevant to us, rather than something that's sort of like a worksheet or something like that. Not that we do that with children, but it's just the best example I can give at the moment. We also want to encourage children to argue their ideas in justifying mathematical and scientific thinking. And again, that's another joy of maths and science, is that we really celebrate whether we're right or not. And I remember being in a great talk with someone once who was talking about maths, and I wish I could remember who it was to give them credit, but they were saying all the great mathematical and scientific thinkers of the world made a lot of mistakes before they got their actual theories right. And that's the joy of maths and science. So again, that's another thing we're really focusing on, creating that culture of not needing to have the right answer, but really exploring and developing our ideas as well. Okay, so we will look at number first. This is one that we'll all be familiar with. And as I go through the different types of learning about number, there'll be language that you can choose to use or not to use. So it will be language, I'll give you examples as we go, but so for example, with one-to-one correspondence, when you're writing up your programming, think about whether that's a useful term to use for you and for your team or the people that you share your documentation with, and but then also whether that's suitable for a family audience too. If you don't want to use that term, then you just describe what it is. So one-to-one correspondence is, before children can count, they need to develop an understanding of that things go together. So for example, being able to put one object on another. So here we can see that if this little girl puts a green bear on the green bear, then that's one-to-one correspondence. If it's in home corner and you're placing a teacup on a saucer, then that's also an example of that. So yeah, here's a great image here where we can see picking up pom-poms with the tweezers and popping them, the number of pom-poms in that to match the number. We also have rote counting, and this is where children learn to count by memory, or they say numbers in order. So you might be really familiar with this as well. When children are learning to count, they don't always get the order right. So maybe they're 1, 2, 3, 4, 7, 9, 10. So that you can see that that's an emerging understanding. So with counting, that's what happens first. There's that understanding of that counting is a thing, understanding that numbers are involved, then it's memorizing the order, and then that moves on to actually understanding that counting has a value attached to it. So if you've got 10 bears out and you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you know the last number you say represents the number in that group. So this means being able to match a number word to an actual item or object. So the number 1, 1 block. The number 2 means 2 blocks. And you would be really familiar with seeing children with those emerging skills. So when children do move on to understanding that what they're counting actually represents a number amount, we call that the cardinal principle. And then another term, just to introduce, excuse me, is when children learn they can count in order, or things have an order, first, second, third, fourth, fifth, we call that the ordinal principle. And I'm sure as I'm reading through these, you can think of so many examples of how you see that every day. We also have subitizing, and this is it's quite it's where you're able to look at how many items are in a group or a set and be able to identify how many it is without counting. So if you saw a bundle of 4 of these counting bears, you'd be able to say 4 without touching each one and counting it out. And that's a skill that also develops over time. But sometimes that also relates to patterning. So we can see here that you know that number 6 is on the dice without counting those 6 dots, because you're familiar with that number pattern there as well. So let's think about what that might look like in practice. And these are things that you will be very familiar with. So when we're supporting counting, just flip slides. So whether that's, rote counting, or whether it's the counting using our fingers so that we have that one-to-one correspondence, we're really reinforcing children's counting skills. Examples here, 5 little ducks. In that one, we can be counting forwards and backwards. 5 cheeky monkeys, we're counting backwards. 1 elephant went out to play, counting forwards. And simple addition along the way too. If we're looking at play that really reinforces one-to-one correspondence, it'd be like in this image here, where we're putting the number of items that match the written number or the numeral. Moving on to patterns. Now, patterns are something that are really important. They're recognized as the cornerstone of mathematics because they enable us to be able to predict. So for a pattern to actually be a pattern, it must have a unit of repeat so that you are able to predict what comes next. So in this one, we can see we've got yellow, black, yellow, black, yellow, black, yellow, black, and we know that what will come next is yellow, black. So if we don't have that consistency, it's not actually a pattern. So we have what we call that element that's repeated, and here it's yellow, black. Now we see this all the time in songs and in stories, in music, excuse me, in elements of design. There's lots of different types of patterns. They can also be growing. So I have an example here where we start off with yellow, black, and then it's yellow, black, black, yellow, black, 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 and so on. So we can see that each time it's growing by 1 black, but it's still a pattern because we're able to predict what's going to come next. And then this beautiful butterfly here is a great example of symmetry. So what might, and then got that image there of an orange. So that's another great example. We can see that that pattern is a continuing pattern. It goes around and the segments are the same. So what this would look like in practice. So you can start with simple patterns with children to help them understand that that basic element is that the patterns do have those same elements that repeat over and over again. So you're helping children to develop those skills when you're asking the questions like, what comes next? Or you're asking them to describe their pattern to you, and then you're guiding them on what the pattern will need. So here we're just, the key thing is that we're reminding them that patterns need to have the same elements repeated over and over again. If they have different elements then that aren't repeated, then it's not a pattern because you can't predict what's coming next. Now, what we also know is that children learn maths best when they use their whole bodies. So patterns are great to explore with movement. They can be things like clap, stamp, foot, clap, stamp, foot, clap, stamp, foot, and so on. Think about making patterns with your body and then getting children to copy them. So yeah, that reminder that children learn best when they can feel mathematics. So the next one down the list of concepts is measurement. And what we do in early childhood is focusing on learning about measurement conceptually. And again, this often uses our whole bodies when we're doing it, rather than using formal measurements like rulers or measuring tapes or things like that. So when we're using formal measurement, it allows us to build that conceptual understanding that we need before we move further into understanding formal measurement. So an example of informal measurement might be 2 children standing next to each other to see who's taller. We call that direct comparison because you're able to look at them and directly compare and see which one's taller. Informal measurement could be something like measuring, children laying down and measuring their length using blocks from the block corner. So they're using a familiar resource and they're using it to see who's, how many blocks it takes to get their length. So here's the basics that we need to understand for measurement. All measurement uses units. So it might be blocks, it might be paddle pop sticks, it might be pencils, it might be children's feet as they're going toe to toe or heel to toe measuring out the length of the room or something like that. We also need to remind you children though that that consistency is really important. So each unit must be the same size. So if you're using pencils, the pencils all need to be the same size, not some big ones and not some small ones. And the way we can sort of understand this is when we look at each centimetre on a ruler, it's exactly the same size. Excuse me. So informal measurement will be the same sort of thing. There's also no gaps between units when measuring. And I saw a great example of this where children were measuring how far they'd thrown something, and they were sort of going heel to toe to measure with their feet. And then some children were sort of taking bigger steps, and other children noticed because there was this, innate sense of fairness and not cheating in this competition. So this is a great way that we started to talk about what we call unit iteration, where we don't have any gaps between the measurement of the units when we're measuring. Another great example in that one was that children realized that some people's feet were much bigger than others, and they realized that it wasn't a good way to measure because it wasn't consistent between them. So yeah, I guess thinking about when we're using informal measurement, it works on the same principle as a ruler or a measuring tape. It has to have that consistency and no gaps between the units. When we're measuring, there's quite a few different areas that we can focus on. So when we're measuring length, we need to have a starting point and an end point. So if we're looking at the length of the room, we might be measuring from the door to the far wall. If we're measuring how far something's been thrown, we need to agree on a starting point and an end point that we measure from. When we're measuring weight, we're focusing on heaviness rather than size, and that you can have I'm sure you've had lots of great conversations with children around that, thinking that larger things might be heavier. When we're looking at capacity, that's when we focus on the maximum amount that something can hold. And this is different to volume. Volume is the amount of space that something takes up in a container, not the capacity of the container. So they're related, but different. We can also focus on area, and this is the amount of space on a surface. And a great way to think about this when we're working with very young children is when we have a piece of paper and keeping paint within the paper or going over the edges. Like these are really simple ways that children start to build an understanding of area and measurement. And time is also a form of measurement that we can focus on. And I think this is a little bit different in that we can't have those distinct hands-on experiences with time, but it does relate to children's personal experiences. We know that children measure the day by key events that happen. So we have those routine times that help them mark what is happening throughout the day. So we have the time they arrive, morning tea, lunch, rest time, afternoon tea, home time. And I think one of the things that we do with all of these things is that we introduce the relevant language that children can use. So let's look at what this might look like in practice. And these would be things that you'd be quite familiar with and that you would say all the time. And I think we're just sort of reinforcing it or reiterating it now so that we can really be aware of how we're including maths in our planning and our assessment for learning, assessment as learning, and assessment of learning as well. So here's some of the language that we use every day. Bigger, smaller, longer, shorter, heavier, lighter, more, less, full, empty. And it's important to remember that this language is something that we use with children, with young children every day too. So thinking about our meal times, for example, with babies and toddlers, we're often talking about, who needs more food, whose bowl is empty. You have a big piece of a carrot, whatever it might be. So we're just being intentional in thinking about how we can really encourage that mathematical language in our conversations as well. So moving on to another maths concept here of space and shape. So when we're looking at space and shape, so if we make those connections with later maths as well, so this is where we have the foundations of geometry, just like pattern is the basis of algebra, measurement stays as measurement throughout. Now spatial, if we think about those spatial language and spatial skills, there's something that, again, that we're learning, that children are learning from infancy. It's a really key part of their development in the early years. They're constantly learning about the world around them. So let's think of some examples that we see of that every day. So we're thinking about children who might be crawling through play tunnels. They're crawling over and under trestles. They're crouching down to get into small spaces. So this involves memory and practice where they're building on their previous experiences and knowledge. But when they're doing this, they're judging distance, size, perspective, angle, position, direction, those sorts of things. So some of the words we might be using with them will be things like on, up, down, through, in front of, behind, next to. So it's any language that refers to position, direction, or location. And with that, we're sort of giving them words and language that goes alongside the experiences that they're having with their bodies moving through space in your environment. So I've included here going on a bear hunt as an example, because I'm sure you're all familiar with the language in that in terms of how that's how that relates to children's movement and spatial skills. Thinking about shape. So when we talk about shape with children, shapes are 2D objects, two-dimensional objects, which means they have a height and a length. So that's things like squares and triangles. When we talk about 3D, we don't use the word shapes anymore to be mathematically accurate. It doesn't matter so much, but just information in case you're interested. So that would be referred to as 3D objects. And that's where we've got like cubes and spheres. So part of what we do with children is helping them to learn those various names and labels for shapes and objects. But more than that, it's really thinking about the attributes of those shapes and objects as well. So whether they've got, you know, the number of sides they have, the face, the edges, those sorts of things. And this will occur in everyday play all the time. So let's consider some ideas then on how it might look in practice. So storybooks are a great way to include spatial language and spatial skills. Not sure if you would be familiar with going on a bear hunt. So we talked about that one before, and that's where children can use their bodies to make that connection between the words and the actions of over and under, through it, that sort of thing. Rosie's Walk is another great example, and I've seen some really beautiful examples from early childhood education and care services where the children have plotted out their own pathway of Rosie's Walk. So it could be any book that you have that focuses on spatial skills or spatial language, or direction, position, and location, and thinking about ways that you can be intentional in embedding that in the things you're doing throughout the day with children. Another thing we can do if we're looking at shapes is thinking about going on a shape walk. So this could be taking a short walk near your service, or even in the yard, to do a treasure hunt for shapes, or just taking a moment to notice the shapes with children. It can be spontaneous, it doesn't need to be a planned experience. And when we're asking children to identify shapes, we're asking them to think about the attributes that they can see. Think about whether they're flat, whether they're curved. For example, the front of a tunnel is round and it's a circle. A panel in a fence has long straight sides and shorter straight ends, so it's a rectangle. We can think about a trestle having 3 sides and 3 corners, which means it's just like a triangle. So it's just these conversations that we can have either as a planned part of the curriculum or just as spontaneous conversations. So we'll move on now to our the maths concept of chance and data. So with this, it tends to be the concept that people are less familiar with. So when we're talking about chance, it's referring to probability. So the probability of something happening or a degree of likelihood. So when we're starting out in having these conversations with young children, it can be as simple as yes, no, or maybe. Or broadening it out a bit, it can be yes, it's certain, it's possible, or it's impossible. So when we do have these conversations with children around chance, some of the things that come up can be really quite amazing. So I'll use this example on the next slide of we're looking at how it could look in practice. And when we're asking those yes, no, maybe questions with children, it could be, will it rain this afternoon? So when we're doing this could be looking out the window, we can see that it's completely clear skies, and children might say, no, it's not going to rain this afternoon. But there could also be conversations about a time last week, for example, where rain clouds came in very quickly. So maybe it is possible. Or maybe they can see a big storm that's about to happen. So yes, it is likely, it's probable. So these are the simple questions that we can ask that help to build that understanding of whether the probability of something happening. Now, of course, this becomes much more complicated further on, but this is the foundation where they're building an understanding. So the question of will it rain this afternoon might be a bit simpler than the next one. So I've had this conversation with a group of preschool age children, and the question was, can dogs fly? Now, initially the answer was no, of course they can't fly, because to fly you need to have wings. But then another child had the idea of, well, what about if you put a dog on a plane? Then they can fly. And that turned into a great conversation about what was needed to fly. Do dogs go on planes? What experience do we have around this? So yeah, it's a great example of how you never really know where children's conversations are going to take you on one part. And the other bit is it's really unpacking all the ideas behind what does chance, what does probability mean. So if we move on to thinking about data. So data is how we find our answers to questions. And whether you are a scientist who is doing a big study on brain development, or whether you're a 3-year-old who's collecting leaves in the yard and wants to know if they have more red or green leaves, you follow exactly the same process. It's about having a question in mind, collecting information in relation to that question, organizing the data that you collect, and then representing it, and then reading what it says or interpreting it. So the EYLF version 2.0 recognizes the importance of being able to organize, record, and communicate mathematical ideas and concepts. So this is from Learning Outcome 4, supporting the development of thinking and learning skills. So you'll be able to see there that that really does align with those aspects of data collection, of collecting, organizing, communicating or representing and interpreting ideas and concepts. So we'll have a little think about what that might look like in practice. So a very simple way, like when we start with collecting data and representing it with young children, we start off using the actual objects if possible. So if it was, in this example here, what types of fruit did people bring in for morning tea? So we can ask the children to put their fruit out, and we sort it into groups to see how many different types there are. So maybe there's 3 apples, there's 4 mandarins, and there's 2 bananas. So we're able to look at those next to each other, count them, work out which one is the most common. If it's looking at, a box of cars or counting bears or things like that, again, the question that we start with is which is the most common color, and then we sort it and represent it. After that, if we're progressing along in representing data, then we can start to use pictures instead of the actual objects. And then that will lead us into the data representation that we see more frequently as adults, which is things like that pie chart that we had right at the beginning of the talk today. That's a way of collecting data and representing it in a way that's really easy to read and to see the message that it's saying. So when we're doing this, this early data collection with children, we're helping them to use mathematical skills of recognizing attributes, comparing, sorting into groups, and we know that that's important across so many different mathematical areas as well. So we're using counting skills, and we're also using direct comparison, that measurement approach that we've talked about before. So I think this leads us nicely into thinking about birth to three mathematics, because there's a really strong focus there on those attributes. So I think I've spent a lot of time reading about mathematics for infants and toddlers, and I find it absolutely fascinating. I'm sorry, I'm just seeing a comment here that there's background sounds. I'll just see if I can, give me one moment. Apologies, I've just, it is quite noisy outside there, and I've just tried to block out some of that sound for you. Hopefully it will be easier. Thank you for that, for letting me know that, Maria. Appreciate it. Okay, birth to three maths. So one of the things here is that the research shows us that babies are born hardwired for mathematical thinking. So that means that they're really receptive to maths from from infancy, basically. And alongside that, the research shows us that these skills and dispositions around maths that children develop in the very early years shape their learning across their lifespan. So it's yeah, it's quite important that we think about how we start fostering maths from the earliest of years. Now, we can do this by being intentional in using mathematical language and acknowledging those mathematical concepts and processes. And really reinforcing with children, helping them to know that they're capable and confident mathematical thinkers. So it's not just about that content knowledge. It's really helping them to see maths as something that's fun and enjoyable and something they can do well. And what that means is looking right back to these precursor concepts. Now, these were developed by the Erickson Early Maths Collaborative, and they've recognized the importance of the first 3 years of life in terms of providing a foundation for mathematical knowledge, understanding, and confidence. And when I go through this, you'll be able to really see how this is something that we do every day with young children. So if we start off with the first one, so with attributes. So this is where we're talking with children and we're giving them labels for things. We're helping them to understand that everything that we touch, so all elements have properties that we can use to describe or explain them. And this is one of the most important foundational skills in mathematics. So we use our senses to perceive attributes. So that can be things like, for example, let's use a strawberry. We can see if the strawberry is the color of the strawberry, is it dark red or light red? We can feel if it's hard or soft, and we can taste if it's sweet or sour. So yeah, thinking about all those conversations we have with children where we're talking about something being red, something being hot, something being cold, something being shiny, smooth, flat. These are the ways that we build an understanding of attributes. And remembering that a lot of the things that we talk about as sensory play are building it as children building an awareness of attributes. We can't do any maths without being able to recognize and explain attributes. Then the next one we have is comparison. And this is where we're looking at things being the same or different based on identifying those attributes. So we're matching things being the same, or we're showing that things are different. So when we're doing that, this is the foundation of sorting and classifying as well. And that leads us into children being able to make sets, which interestingly is the foundation of multiplication and division if we want to get a bit ahead of ourselves. But right now, thinking about infants and toddlers, just being able to see things as being the same or different is such an important foundational skill in mathematics. With patterning, this is about sequence and regularity with very young children. So this might be noticing patterns in nature, or it could be storybooks as well. So if we think about that rhyming and the repetition that children will see in stories like Harry McClary, or use our example of going on a bear hunt again, that patterning or that awareness of sequence is also really important for very young children. And we also see patterns in music and song. So this is where from infancy, children are building that foundational understanding. Now, all of these concepts build on each other. So after we get to patterning, then children start to notice change. So this is when they're able to recognize, because they can compare attributes, that they're seeing that things have changed in some way. So this might be something like they might notice that they've pulled apart two triangles in blocks, and that makes when the two triangles are together, it makes a square. Pulls them apart, it makes a sorry, I've lost my train of thought there. You know what I'm saying? So they might pull the blocks apart, and they've got two triangles. Put them together, they've made a block. So it's about it's about joining, taking apart, that sort of thing. So thinking about, for those of us who work with very young children, it's being really mindful about how we can support those precursor concepts consistently throughout the day. So the research shows us that even if educators don't feel confident in themselves as mathematical thinkers, or also as families as well, when we can, especially if we can reinforce with families the importance of these sorts of things to develop important math skills. So we're in a really good position to be able to build confidence in people and to be able to change people's perspectives about maths in general and about the importance of maths in the early years. So some of the things that we can do, if we build our own understanding of children's mathematical thinking and learning across the early years, we can focus on being intentional. We can focus on planned experiences and spontaneous experiences, and we can advocate to families to let them know that the foundational skills that babies and toddlers are developing are really important foundations for mathematical thinking and learning. Yeah, I think so. I've just reading my notes here. I've pretty much gone ahead with what I wanted to say. So the last point was just about families, but I've already spoken to that point. I think it's so great when you can bring families in and remind them of how much they're already doing with children as well. Okay, I'll just pause for a moment there, because our next thing that we'll be looking at is an interview with our wonderful educator, Rachel. I can see that a few people have their hands raised. We will do questions and answers at the end, but if there's anything that's sort of really important to discuss before we go on, if you wanted to pop it in the chat, I'll be able to respond to that. And what I'll do is I will start our interview with Rachel. Hi, thanks for joining us, Rachel. Today we'll be talking about your experiences with teaching maths and science in your family daycare service. So thank you. Thanks for joining us.
You're welcome. Thank you for having me today, Kelly.
So starting off, we'll talk about maths and science, but thinking about maths first, how do you feel about it?
Well, as I was just briefly saying to you before, growing up, I found maths really hard. But once I started a uni course with maths, I found that teaching maths to little children actually came quite naturally. So I I feel that children aren't aware that I'm actually teaching them maths, but we do it in our everyday learnings. So such as singing number songs, counting games like What's the Time, Mr. Wolf? We do that quite. I have a group of children that regularly ask to play these group games, and so they're not aware that they're learning maths. But when you say what's the time, Mr. Wolf, and Mr. Wolf turns around and says 5 o'clock, and then we're taking 5 big steps to the wolf. So I believe they're learning the basic concept of math skills through those games. We play bingo matching games. Um, how many times you can bounce the ball, how many times can you catch the ball, and we count that. When we sing happy birthday, if it's someone's birthday, we might do 3 claps because they've turned 3. So I just think any of those activities are incorporating maths into the learning experience, and I feel that by doing these activities, the children are being introduced to these very basic maths concepts. But I think it just builds on it as they grow older. It builds on those foundations of learning.
Great. So you were saying that initially you didn't feel so confident about maths. Was that because of school or?
Yeah, growing up, I was never very strong at maths, and when I started doing my Bachelor of Teaching through uni, I did a few maths subjects, and I had to read everything, and I had to cover everything to understand everything. It was like going back to basics and learning how to do maths again as a 7, 8 year old. Luckily, I had 3 children, and they were in primary school, so I kind of used them as my guinea pigs, and I worked really hard. And then I found a new love for maths, and I didn't find it as overwhelming as previously when I'd think, oh, how am I going to introduce maths into, how do I introduce this concept with, 2 to 5 year olds? I felt that was very challenging, but after doing the course, I was able to walk away with ideas and strategies to put into place to aid the children in my care and introduce maths as a very basic concept. So, yeah.
It sounds like you discovered a real joy and sort of love of maths along the way. So
Yeah,
that's
yeah,
great to hear.
yeah.
When you think about how you plan for maths experience in your program, what sort of things are you thinking about when you're planning?
I want the activities to be engaging, so that promotes like the a basic math concept through play and exploration. So counting activities, counting objects using toys or blocks or natural resources such as rocks, and asking the children to count them into groups, especially if they're like 4 and 5 year olds and they're quite interested in, telling you how old they are, showing you how many fingers that is on your hands. Well, then you can introduce objects to show number counting that way, and counting songs like Five Little Ducks, Five Speckled Frogs. Like I said before, What's the Time, Mr. Wolf? So all those are activities that I would put into my weekly program with my children.
Brilliant. What about thinking about those sort of unplanned experiences, things that crop up throughout the day where you see something happen and you think, this is a great moment, I can step in. How do you intentionally consider those moments and support mathematical thinking and learning?
First of all, I would stand back and observe what was happening, and be attentive to the spontaneous moments where the mathematical concepts are naturally arise, such as counting items or measuring distances, or when children are recognizing a pattern. I would just in their everyday learning, I would encourage them to further create that pattern. But basically I would stand back, observe what's happening, and then I would engage in some open-ended questions with the children, asking them what they think is happening, what can they see, and trying to encourage them to critically think about what's happening in that process.
Brilliant, thank you. If we look at the same questions, but just shift the focus to science then now. So how do you feel about science yourself?
Well, once again, I was a little bit overwhelmed with science, but we looked at Science Week earlier this year, and it was actually a really rewarding week. I made a volcano with my children. So I had a big a 1.25 litre soft drink bottle, and we ended up getting Play-Doh, just a tanny coloured Play-Doh, and we made this lovely volcano, and we filled it with vinegar and bicarb soda, and we put food colouring in, and we made this amazing volcano. And so we actually did that every day, multiple times, with lots of vinegar. So I felt like it allowed it sparked like a curiosity in the children watching the experiments happen. So I definitely found teaching children science not as challenging as first on. And I think the main thing is to make sure those science experiments are always hands-on. So for another example, we got milk, and we added everyone had their own bowl, and they all had their own food colouring, and we put a little bit of food colouring into the milk, and then they used cotton buds to swirl it around and see what happens. And another one is, once again, milk in the bowl with the food colouring, but then if you use washing detergent and you drop it in, and the food colouring kind of, what's the word, just makes it splurge everywhere type thing. So those, using these hand-on experiences allows children's curiosity to, run a little bit wild, and the excitement in it. So I think doing hands-on experiences is definitely the best way to introduce science into your learning environment for little ones.
Yeah. And it sounded great, giving them the opportunity to come back and do it again and again and again.
It went on for a good solid hour. I think the volcano, we just kept adding the vinegar and the bicarb soda, and then they were tipping it in as well. And yeah, the little explosion, the excitement, it was amazing. So
what were some of the conversations or some of the observations that children had around that?
So most of the conversations were, do it again, let's do it again. When mummy came in to pick them up or daddy came in to pick them up, they wanted to show their parents what we'd done. Can we go home and do this? And so I was just telling the parents exactly what we did. So then on the weekend, when they had some more time, they would go and get vinegar and bicarb soda, and even just tipping it into a glass cup. You don't need to make the whole volcano. You get the same reaction from the child, whether it was in a volcano or a glass cup or a bowl. So so that was a lot of the conversations around that, and just the children engaging socially with each other in all the experiments was really lovely.
Yeah, no, that's brilliant. And it's great to hear that you were able to make that connection between your service and home as well, that children were so excited that they took it home. Yeah, that's brilliant. So you've talked a bit there about using things like Science Week to help give a bit of a focus for science programming, but what other ways or how else do you plan for science in your program?
Let's look a few little notes. So I think planning science experience involves setting a clear objective into my service, and it's, I guess, incorporating hands-on experiences, observations, watching what the children's reactions are, working out what they think, and then using this as an inquiry or question then I think using the inquiry as a questions and developing open-ended questions with the children to see where their thoughts and ideas develop from as well. I don't know if that's really making sense if I'm coming across.
Yeah, no, it does. That's great.
Correctly.
It sounds like there's a lot of conversation between children, a lot of interaction, and a lot of sort of inquiry taking place.
Absolutely. So it's just I think when it comes down to it, I think whether it's science or maths, it has to be hands-on. You can't sit there and expect them to learn through just talking to them. You have to physically be doing a hands-on activity. And I don't always program those. I find that it happens just naturally throughout the day, and you've just got to take that time to observe and then implement then and there on the spot, because otherwise I think you miss those learning experiences if you go, oh, I'll program that for next week.
Definitely.
That concept in their little mind may not be there then. So
that leads really nicely into our next question, which is how you are intentional around those moments when the unplanned experiences crop up. So do you have any examples or thoughts on that?
I I think just taking it in the moment, like making sure that in that moment of time, when you see those intentional learnings pop up, run with them. So whether it was, so for instance, we'd only planned to do for Science Week, we were only really going to do volcanoes. But once I realized the excitement and the engagement from the children, that I had 2 and 3-year-olds sitting at the table for longer than 45 minutes and was maintaining their attention for that length of time, I realized then that I had to find some other activities that were a little bit different, obviously science-based as well, to bring in the next day and implement those into our learning, because I didn't realize how much interest and how engaged the children would be in it. I thought I'd just put the vinegar in and put the bicarb soda in, we'd have a volcano and half of them would walk away and not be interested. But the engagement and their inquiry into the whole learning process and why was that happening? So then I had to break down, because we're adding the vinegar and then we're adding the bicarb soda. And when those two mix together, it makes a big explosion. So I think I just ran with that learning process, that I thought, well, what else can I do? And that's where I ended up with the milk and the food coloring and the dishwashing liquid. And so from then on, after that, even once Science Week finished, we still continued to look at different experiments and see what happens when you mix things and do things. And so even now out in our water play, instead of just putting water in there with the sea creatures, I've actually added ice cubes and food coloring to our water and sand in one section. And I noticed that the little ones quite like to watch what happens to the sand when they pick a handful up and throw it into the water, instead of saying, no, sand's over there, water's over there, like just really engaging in making those connections of what happens when we add something to something else. And so so it's kind of like making mud pies. They all love to add the water to the mud and make a mud pie, but they don't get the opportunity to add these different ingredients together normally to see what happens. So anyhow, I hope that's
No, that is brilliant, and it brings us to the end of our questions. So thank you so much. There have been great examples and it's been a really great chat. So appreciate your time.
Welcome.
Thank you.
Thank you, Kelly. Thank you.
Okay, so I loved doing that interview. I think Rachel's enthusiasm and ideas, you can almost imagine the excitement at her service with the children doing those experiments. And I think that leads us in really nicely to looking at science in the early years. So this is an example of what science is in these pictures here when we're working with young children. So we've got this picture of the little boy on the bouncing thing, like he's exploring gravity, he's exploring so many different things, like how the air's moving around him, all sorts of things. This other picture here, this little boy was 2 or 3 at the time, and he's pointing to this close-up is of an ant. So what had happened was he dropped some of his biscuit and the ant slowly dragged it away, and we had to watch for about, I don't know, 10 minutes as the ant did that. And the conversation was amazing. So these are the moments that we see happen every day that give us the opportunity for really rich, beautiful scientific exploration. So what science isn't? It's not just lab coats. So quite often if we Google science and children, or if we're looking for ideas, we come up with these well-meaning images which are children who are dressed as lab scientists, but that's not where a lot of science happens. So just being really, really aware of that. Oops, sorry, I've jumped ahead. So what similar to maths, we have science concepts that we focus on. And again, they're not unique to early childhood. They underpin all scientific thinking across everything. So we have physical science, earth science, chemical science, and biological science. And what we do, sorry, one sec. When we're exploring science, we're using our senses as well. So we have seeing, hearing, smell, touch, taste, those sorts of things. And we also know that we can use technology to enhance our senses. So that can be using things like digital microscopes, or it can be through photography or through video, where we're able to watch things in slow motion or listen to sounds more clearly. So, and again, similar to maths, we have science processes as well. So this is where we're observing, we're describing, we're asking questions, we're explaining. And if you think about this is pretty much what we do every day when we're working with children. It's a constant process of exploration and inquiry. So it's just being intentional around that, and yeah, making sure that we're making those connections with science. One of the really amazing things for us as educators working with children is that we get to be co-learners alongside children. And that means we don't have to have the answers to everything. So the EYLF, in terms of responsiveness to children, the EYLF notes that we are building on children's previous knowledge, their strengths and their interests. We're making the most of planned and spontaneous teachable moments, and that children and educators learn together. So they share decision-making in ways that are respectful and trustful. So it also aligns with sociocultural theory as one of the theories that's outlined in the EYLF version 2.0. And in this, it focuses on the social nature of learning. So we look at the fact that we can be experts and we can be beginners alongside children. And sometimes it's children that bring that, the ones that bring that expert knowledge in. I can think of an example from just a few years back, playing with some children in Block Corner from some research I was doing. Started off with building rockets. It ended up with them building models of the Earth and showing all those different layers of the Earth. And the educators were astounded that children knew about the mantle and the core. And they brought this amazing body of knowledge with them into the service. So I guess something we touched on earlier, but to remind ourselves here, is that it's okay to create a culture where it's okay to be wrong. So what we're doing is we're coming up with hypotheses, predictions, we're testing our ideas, we're learning new knowledge. And we're coming together with children to combine our knowledge to answer our questions. Let's start off by looking at physical science. So here we have 5 big ideas of cause and effect, movement and force, gravity, magnetism, and energy. And again, these will be things that you're really familiar with seeing children explore in their everyday learning and play at your service. So cause and effect is simply thinking about why something happened, which is cause, and what actually happened, which is effect. So this will be things like a child will realize that if they push their car down the ramp harder, if they apply more force, it will go faster. So that's the cause and effect. Now that ties in nicely to the next one, which is movement and force. And that's understanding that one object can have an effect on another object. So when we're pushing someone on a swing, and the movement is what happened when force is applied. Again, the swing is a great example there. Or if we see this little baby in the picture here who's going to push this car down the book, it's going to slide down and they'll realize that they've created that to happen. If we think about what this might look like in practice, so we know that water play is a great opportunity for exploring so many different scientific ideas, but a simple example here is for children realizing that their action makes something else happen. So in this picture, this child was pushing their hand around and it made the water move, and then that made this paper boat that they'd made get wet, and then the paper boat sank. So with that, the movement of the water was something that made the paper wet and made it sink. So when we're looking at physical science, so this is, I'm sorry, still thinking about physical science, we're looking at gravity and force. Sorry, gravity as a force. So gravity is something that we can't see, but we know that it has an action. I'm sorry, excuse me 1 minute. So we can go with the NASA definition of gravity. They're saying it's the force by which a planet or other bodies draw objects towards its center, and the force of gravity keeps all of planets in their orbit around the sun. But more simply, when we're talking with children, we could think about it as a force that we can't see, or it's something that keeps us on the ground. It makes things fall, or it pulls things together. Thinking about how we can explain magnetism to children. And this is quite simple because it's something that we see in magnet play as well. Magnets, we know, pull things together, or they repel, which is pushing things away. So the scientific language that we can use here is attract and repel. And if we wanted to explain that to children, we could talk about the forces between opposite poles. Now, there was a comment earlier on from Louise who commented that we shouldn't be afraid to overcomplicate it, that kids love that. And I think that's a really important thing to think about, that we can introduce this complex language, complex maths, science ideas, and children will really, not all children, but some children will really welcome that opportunity to extend their thinking in those ways. If we think about what this might look like for children, it might be, sorry, just thinking about that last one, it might be as simple as a baby dropping food from a high chair, jumping, thinking about how long they can stay in the air. But I've flipped onto the slides to think about energy. So here we're looking at the language we can use around it as well. So we have potential energy and kinetic energy. So potential energy is stored. So if you pull a child back on a swing, that's stored energy. Kinetic energy is when you let the swing go and it moves. Whether you might think that's relevant for young children or not, I'm not sure if anyone's ever seen the show Blaze and gosh, I've forgotten the name of it now. There was a show around cars and they would unpack very complex science ideas, but it was aimed at 3 to 5 year olds. So I think that, again, we can introduce this language with children. We can explain these different scientific ideas. We also know that light is a kind of energy, a type of energy, and a really great way to explore this is through shadows. So we know that when something's solid and it's put in front of a light source, the light can't get through, the light is blocked, and the word for this is opaque. The object is opaque. But when the object is transparent, light can get through, so like glass in our windows. And when an object is translucent, like cellophane or these coloured blocks, the light filters through partway and creates the coloured light that we see. We can also know that if we move an object closer and further away from the shadow, it gets smaller or bigger. And that's because light has beams that are bent when they hit that object. So what might this look like in practice? A great example for that is thinking about how we can explore shadows. And this is, I'm sure, something that you've had conversations with or intentionally included in your service quite frequently. So an example of what you could do to really explore it would be to use some torches or flashlights and different objects in a slightly darker space. So you're encouraging the children to shine the torch against the object and ask what they notice. So the science here is, as I just mentioned, that light travels in a straight line, a light beam. It can't go through a solid object, so it bends to the side, and the shadow is cast where the light can't get through. And you can do some great exploring of moving the beam further away and closer to the object because it bends the light differently. And that's when we get big shadows or small shadows and fuzzier shadows and clearer shadows. So there's lots of things to explore there. Moving on to our second concept of earth science. Yeah, there's a great comment there of shadow animals using your hands. Yes, really great example. Now, when we're looking at earth science, these are things that children have a lot of experience with. It's air, water, weather, rock, sands, mud, soil, those sorts of things. And these don't need to be an overly complicated understanding. It's more a process of acknowledging and investigating the things that are all around us in our everyday life. So if we look at air, so one of the interesting things about air is that we know it's around us, but we can't see it. So how do we explore that with children? So we know it can move things. So we're looking for that. We can be looking for how the wind blows things like wind chimes or this windsock or a kite. But some of those things we won't be able to see, and then we'll have to explicitly explain for children. So understanding that air is important for living things. So we can experience that with our bodies. We know we breathe air in and we breathe it out. Thinking about water. So we had some great examples of water play from that interview with Rachel as well, thinking about how we can think about how water has weight. We can think about how water, how things float in water and what that means and the science behind it. We know that water goes up in the air, and we also know that it comes down as rain, sleet, snow, and hail. Water can change form, so from ice to gas and back again. Water clings to itself. That's a really interesting thing to observe. Like when you look at water droplets, they group together into water's like a little bubble when it's in a drop on the table. And we also know that water can act as a solvent. So in this picture here, this is a great experience. The child had emptied out a tub of water and was watching how it was absorbed into the concrete and was evaporating as well. So I think a lot of what I mentioned before, a lot of what we do in science is around sensory play as well, and thinking about how we now just shift the lens a little bit to think about how that's science. One way to explore the properties of water is looking at those three states that it can be in. So liquid, solid, and gas. And yeah, Rachel had mentioned in her interview that idea of making ice cubes and including those in play. So that's a really great way to do it as well. We can ask children to share their understanding. They might know what happens when we put a tray of water into the freezer. It turns into ice cubes. We can also then ask them what will happen when we take that ice out and think about when we leave that ice in different areas, what might happen. And we can provide that scientific language for children about water changing state, that it's a liquid and a solid. We'll keep moving forward. Sorry, slide through there, because we do have a lot to still get through and I'm mindful of the time. But I really think with water in particular, there'll be so many different ways that you can think of how children experience it. So they swim in water, they drink it, they bathe in it. They'll have lots of different understandings and lots of information that they'll be really keen to share with you. Now, another thing that children have often expert level knowledge of is rocks and sand and soil. So when we're looking at rocks, it's thinking about how we can explain these to children when they come to us with questions. So what is soil and what is sand? So we know that soil is broken down rocks and plants. Sand is broken down rocks, so when they erode or wear down over time. And mud is where soil or sand is mixed with water. So thinking about building those understandings as well. We can also look more deeply at rocks. There are three main different types. We have igneous, sedimentary, and metamorphic. Now, igneous rocks, like this black one over there, are formed when hot liquid rock cools and becomes a solid. Sedimentary rocks are formed when sediment collects over time at the bottom of lakes and the sea. And metamorphic rocks are ones that were once igneous or sedimentary, but they change over time due to heat or compression. So we can use this scientific language with children. Excuse me. If we think about how easily children learn complicated multi-syllable dinosaur names and build that deep understanding of that, I think that's a really good indication of the kind of language that they're ready to use and the kind of information that they can quite often really welcome. I'm sorry, I've got a cough at the moment. So one way that we can explore rocks with children, I guess the way that really stands out is that children may bring rocks in. I know in my house with my children, we have rocks everywhere, and they're a great talking point. The way that we learn out more about these rocks is by looking in picture books. They can be looking at websites, and that process of asking questions and comparing, looking for the attributes of the rocks. Are these similar or different to the ones that we can see online? Building more information about them. And this comes back to another great example of how we can be co-learners. If a child's speaking with you about the rock that they've got and what you know about it, you might not know very much about rocks. I know I'm no expert, but we can explore together to find out what it is. So then thinking about what this might look like in practice. So that's the things we've talked about are a really great example of things that we do all the time with children anyway. So we're recognizing children's expert knowledge with the rocks that they have. They've made a really good, so that they would have already looked at their rock, they would have already felt it, they would have already looked for elements of it that they can talk about. So they have some degree of expert knowledge already. We could be a co-researcher alongside them to explore those rocks. And I think another thing that we're doing here too is that when we're using the internet, for example, to help children research and find ideas and information, we're actually supporting their digital citizenship. So we're modeling how we search for things. We're modeling really effective ways to look for quality information and to understand that information. Moving on to chemical science. So this would be the equivalent of what we would see as chemistry at school. For us, working with young children, we're focusing on a lot of great fun experiments, just like the ones Rachel explained to in her interview. So we're looking at matter, whether things are solid, liquids, or gases. We're looking at constancy and change. So this is that some things stay the same, but some things are different. So for example, a block will always stay the same for most of the time, unless something bad happens to it. So a block won't melt, but an ice cube will. And we're also looking at chemical reactions. So the example of what happens when we mix things together, what can we see? Before I go on to liquids, I'll just jump back to here because a really key thing to understand here is the idea of matter. So matter is absolutely everything. It's everything that is around us. It has mass, it takes up space, it reacts and influences other things. So matter has properties and characteristics, and we use our senses to describe them. So are things shiny, smooth, rough? Are they big? Are they small? Are they thick? Are they thin? And we're thinking about how we can combine matter as well. So for example, like mixing ingredients together to make a cake. When we're looking at solids, they hold a shape without any help. So for example, a table remains a table. If we're looking at Liquids, we know that they can flow, but they can also be contained and that they take the shape of a container. So these are great experiments to do with children as well. If you fill a glass jar with blocks, it doesn't take the shape of the jar. You've still got spaces in between, but if you fill it with a liquid, it settles to the bottom. Gas, though, it has no fixed shape and can spread. So if we put it in a jar, it will disperse throughout the jar. Okay, so thinking now about liquids. When we're exploring liquids, one of the great things to do is exploring sinking and floating. So this is a little bit further on from the cause and effect with this child, this little boy with his water experiment. So he moved the water, it made his paper boat get wet. It then started to sink. So he flattened it out and he realized that when he made a flat piece of paper, it floated more easily than the bunched up piece of paper. But after a while, the paper got too wet and it became mushy, and that was the end of that. So we realized that the properties of the paper changed when it absorbed the water. There was the idea that a bunched up item didn't float as well as a flat object or flat item. So yeah, it just from a little experiment with some paper and water, there were so many different things happening. Now, I won't go too much into these. This information is in the booklets that came out. So you can read into this a bit more, but this is something we can also talk about with children. We can talk about solutions. So when we dissolve things in water, like mixing in salt and water, we can talk about suspensions. So that's where, say we mix sand and water and it separates slowly over time, but for a while the sand in that murky water sits there. And then there's this other one called colloids. And this is where the particles are suspended. So if you mix jelly crystals into water, it dissolves and then those crystals stay suspended, which is what makes the jelly. So let's look at what this might look like in practice. So we can provide lots of opportunities for children to mix things around and see what happens. So does sand and water mix? If not, or what happens when you mix them together? Or what happens when we put drops of food coloring into a glass or into the water play trough? Does it mix through? Does it separate out? So we can think about the language and ideas from that previous slide, thinking about solutions and suspensions, and we can start to introduce that scientific language for some of our children as well. Now, the last the last bit in this section that we'll think about is chemical reactions. So that volcano experiment is a great example of a chemical reaction. When the bicarb soda and the vinegar mix, they react, which creates gas, which makes it bubble. So we can observe chemical reactions, and when a chemical reaction takes place, the two elements can't go back to their original form. Their atoms are rearranged, which is one of the really interesting parts of it. We can think about this example too, is that cooking is a chemical reaction. So we mix the ingredients together in the right quantities and we make cookies, but the heat is required to form them into those baked cookies, and they won't react the same way if you don't cook them. So even though we don't necessarily need to explain all of this to children in that much detail, it's still experience that they're gathering about chemical reactions and changing properties. So what might this look like in practice? So I think a great example is the bicarb soda and vinegar or lemon juice. So what we're doing is we're mixing a base with an acid and it's creating that explosion or that reaction. Now, it's referred to as the volcano experiment, and I think it's really interesting to also talk with children about the fact that this isn't actually what happens in a volcano. This is a great example of a chemical reaction, and we can also talk with them about, if that interest then comes up about, well, what does happen in a volcano, then you can move into talking about that, which then might lead into igneous rocks. So you see how things will flow into one another as well. Okay, and I think the last one we have to focus on tonight is biological science. And what this the main thing that this focuses on is looking at the differences between living and non-living things. And it includes plants and animals and the human body. Now, a really interesting part of this kind of science with young children is that they will often think that things that move are living, like the clouds or the sun. And we know that this something called animism is a really common part of childhood. And Piaget describes this, the theorist Piaget describes this as a really normal phase of cognitive development, thinking that non-living things are living because of movement. But I think it's a really good time for us to be mindful about science and young children, because we do often talk about the magical qualities of things, or we give personality to non-living things. So for example, we might say things like, it's time for the sun to go to bed. And you can probably think about lots of stories and songs that do that sort of thing as well. So for us, it's a balance between encouraging that scientific thinking and scientific understanding, but also considering the place for ideas of magic and wonder when we're working with young children. So let's think about some of the examples of living things. So animals as living things. Children will generally have a great experience with this through pets, people, insects, birds, that sort of thing. It could be sea creatures, could be reptiles. They'll also have experience of plants as living things. So there'll be lots of things that they'll be able to observe, but also things that we'll be able to explain to them as well to really develop their knowledge a little bit further. So we know that seeds come from plants and fruits and vegetables, but they grow into plants, or sometimes they grow from roots. And children will be able to see that when plants have light, they grow better. We can help them to understand that they need air, that they need compost, and remind them that they lean towards the light. So what might this look like in practice? Again, we can do things like nature walks or in the yard looking for living things. We can look at, around the community. Children might have observations from home and encourage them to think about what those living things need to survive. So do they have, so these are just some examples from things that I am familiar with from my home setting. We have lots of cicadas, we have lots of brush turkeys and lots of trees. So it would be easy to have conversations around what these things need, because we observe every day these things going about their day. You'll be able to think of lots of examples of things that would occur in your environments, and how you can use these to encourage those conversations with children. So to sum up for tonight, what this means for us as educators. So we need to build our own confidence and remind ourselves that we don't need to know everything. We can shift our preferred lens. So if we're seeing sensory play, if we're seeing language play, every educator has something they're more confident with. But if we can try to shift that to include a maths and science lens as well, that can be really helpful. Thinking about ways that we include it in the curriculum, either planned or spontaneously, and also thinking about advocacy. How can we talk with families about the science and maths that we see every day with young children, and the science and maths that they're able to do with young children too? Oh, sorry, I skipped over there. So what we might do now is open up to some questions. So while we're just looking through comments in here, or any questions that anyone would like to ask, just a reminder that you can join the PD in Your Pocket community of practice on Facebook. So just go in and type PD in Your Pocket and find them there. You can also watch this session again or the previous sessions by hopping onto the website. That link is there in the slides as well. There's a comment there from Amanda about adding in mathematical and scientific language in conversations with children. Yep, that's exactly right. As you've noted, they are everything that we're already doing, and it's just finding those moments to extend on it a bit there. So that's an interesting question there. And how do you explain a dead insect or animal to a toddler? So we know that children under the age of 8 don't necessarily have a firm understanding of the permanency of life and death. So I think conversations around that would be probably quite simple, explaining that it was dead, and thinking, yeah, it's quite a tricky one, especially if the toddler's distressed. But one of the things that we do talk about with biological science is talking about life cycles. So it could be a way to lead it into that, to thinking about life cycles of animals or life cycles of plants. Yeah, I think that would be a good way to discuss it. There's been a lot of comments coming through with people really acknowledging just how much they're already doing themselves in terms of including maths and science. And I think that's wonderful. That's the main purpose, I think, of one of these workshops, is to reinforce how much you're already doing. Sorry, I've got a question here. How can you support a 2-year-old who seems to have a very advanced understanding in maths concepts? He can count to 20 already and recognize numbers randomly. So I think with a child like that, like with any child that we're working with, if we look at what their knowledge is at the moment, where they're at, and then build our understanding of what comes next and think about how we can help them to get there. But I think one of the things with maths that's so important is thinking about those foundations. So here, recognizing numbers randomly, so we know that's that very early, maybe rote counting. So thinking about how we can continue to support that, and then thinking about that next step of making that connection of understanding that the numbers are associated with an actual amount. More ideas for school-age children. So that's a great idea. Good question from Sarah. I will follow up with that and share that information on the Facebook page for you. A great question here from Anna as well. We do maths and science every day, but we don't name or label it. So how can we be more specific in planning maths activities? So I think it's similar to what we're saying in response to Jane. So learning how to identify that maths. And sometimes when we're using maths language, that's the way that we ourselves realize that it's a maths learning experience. So if we're starting to think about if we realize we're saying things are bigger or smaller or heavier or lighter, it can be a reminder to us that, hey, this is actually maths. And then we become more intentional in shifting to that maths lens. Okay. I've just got one more question here that I'll look at. Some specific types of natural materials that work best for teaching maths and science concepts to preschoolers. I think this is a great one if we're thinking about what we can see in our everyday environments. Thinking about, loose parts play. I think if you're looking at using a bought resource, like say counting bears, thinking about whether you could be using stones or something more natural with that as well. But that might be another great question to post in the Facebook page too, to get some more feedback there. So thank you all again for coming. We'll wrap up the session now. I hope you all have a great night. Thank you.